Thanks everyone for joining us. We're Group 5 and our senior design project is an electric pull-down clamp. I'm Joe.
I'm Blake. I'm Jack.
And our advisor is Dr. Rosado.
So here we have a 3D render of our clamp. You can see the blue is the bottom housing, covered by the gray top plate, and then there's our clamp arm with the bolt and an adjustable knob for moving it up and down.
And then just to give you an idea of how this clamp can be used in an industry setting, it'll interface with a PLC, programmable logic controller. The PLC will send it a command to either open or close. I'll take you through the closing procedure. So when the clamp is open, the PLC sends a command to close. The clamp will close at a high speed until it contacts the workpiece. And then once it contacts the workpiece, it will slow down its speed and then increase its torque and force. And then once it's fully closed, done with this procedure, it will then output back to the PLC that it's closed, and the PLC can proceed with its next instruction.
So for the introduction, when we started this, we were researching clamps, work holding clamps, automation clamps, and we found that most of them were pneumatic, which requires compressor, air lines, other components, and it takes up a lot of space. So we wanted to work on an electronic variant, which would be in a more compact package and be easier to integrate to a system. And this will utilize a rotational motion with a stepper motor into a worm gear setup versus the linear motion of a pneumatic clamp.
And just to give you an idea of how many components we're producing by switching to electric. So the pneumatic one, you have the clamp itself, then you have to run air lines, valves, fittings. Your compressor, you have to make sure that's able to handle the added capacity. And then you also have to have sensors to say whether to the PLC whether or not it's open or closed. Switching to electric, you just have one multi-core cable and a 24-volt DC power supply. So greatly reducing your setup times, the cost to set up, and simplifying the whole system. And then that takes us into our requirements. For our clamp, we wanted to provide 100 pounds of clamping force in the closest position. We want it, of course, to be electrically actuated, switching from pneumatic to electric. And then we want to be transmitting our power with a worm gear set. The worm gear set, the decision on that is basically if we want to change our scale, maybe scale it up or scale it down, the worm gear set, there's multiple off-the-shelf gears that you can buy and change your scale as needed. And then, of course, we want to provide maximum force only when the clamp contacts the surface. It's just kind of a safety feature, and also we want our cycle times to be as low as possible.
Alright, so for specifications, how we wanted to start it, we selected our worm wheel and worm gear based around our motor specifications and the force calculations that we made. And we also wanted to have the clamping arm to have between 110 degrees and then -10. So all the way up at the top, 90 to the horizontal, and then all the way down with a little bit of variance based on workpiece thickness. You can also adjust that with a nut too, but just to be able to make sure we're getting the full range of travel with the clamp arm each time.
So then getting into the specifications for the electrical part of the project, we're going to have Arduino Uno to serve as the integrated controller for our circuit. Then we're going to have the 24 volts motor driver to provide the power to the motor. That motor is going to be designed to control the movement of the sucker motor, which two different phases. So each phase actually, the current direction could be reversed, allowing a precise control of the motor's rotation and also range of current flow through the phase. Going down to the NEMA 17, that's just the one we found in the market. It's going to be best for us because that's going to provide the most relatively high torque and precise speed, corresponding to the other motors we're looking at online, and really give us the most torque that we needed. And we're going to be using the cell stepper library to control our Arduino. We figured that would be the easiest for us to use because we could track the motor position, the motor speed, and the acceleration. And of course, we're going to have the on-off switch to ensure safety for the user in case anything bad happens to it.
And then this is our work breakdown structure. The colored in blocks are work that we've already completed, and then the ones that aren't colored in we have still yet to do. A couple highlights, placement in the design section. So the high-level assembly is completed, a wiring diagram, and then also we've done some calculations on our worm gear. Here's our schedule. We're largely on schedule right now, maybe a couple days of slip, but we anticipate that we'll get back on the coming up breaks. And then here's our budget with our whole bill of materials. We are about $60 over budget right now. That's going to be one of our goals in the future to get that down under $500. We do get the benefit of a couple provided components like the Arduino and hopefully wire and smaller electronic components, LEDs, things like that.
All right, so for the mechanical design, you can see the picture here. The top one is the drivetrain, which we'll insert into the bottom housing. And then here's an exploded view of the bottom housing, top plate with the electronics and the clamp arm. So when we were designing this, we wanted to really minimize the footprint and maximize the force output we could produce. So started by researching motors, and we landed on the NEMA 17 for, like said, the high torque output, and as well as a compact package. And budget-wise, it was for a good price range. So once we had that selected, we could kind of design the rest of the system around it, pick which worm gears we wanted based on the size and calculations, and then make mounts for it. You can see the motor mount right there and the worm mount, and those will connect into the housing. And then here's a transparent view, and it's looking inside the housing. You can see the drivetrain in there, and the top plate with the electronics. And just design this housing around all the components. One, again, try to minimize space so it can be easily integrated into a product line. And yeah, just minimize space, keep it as small as possible. This is the top plate that can mount into the bottom housing, and it contains the Arduino on the bottom there and the driver on top. This is kind of made so you could assemble it piece by piece. You could put the Arduino in there with the spacers, wire it all up, and then put the mounting plate and the driver on top of it, wire that up. And then you only have the leads that you need. You don't have the wires that need to go to the motor. And then in the bottom plate there, you can't see it on the back side, but there's a through hole that allows the wires to go to the DC power supply. So those are the only wires that will be out of the system. And then once you have this assembled, you can take the two halves, the bottom housing with the drivetrain and this, and then assemble them, connect the wires to the motors, and then just assemble them with 4 screws. And you can easily take this apart for maintenance and any troubleshooting you need.
And then here's some calculations of the worm gear set. This is to basically figure out what output force we're going to be able to get with our motor's specified maximum torque. Long story short, so 151 pound-force inches. The worm gear set has an advantage of you can get a really high gear ratio in a compact package, but of course that does come with the downside that it does introduce a lot of sliding friction, so that does decrease your efficiency. The sliding friction term shows up in equation 5, where it's subtracting the friction there.
So here's a graphic made of the clamping force versus moment arm, and you can see it's inversely proportional relationship between the force and the moment arm. So this is the front view of our clamp. So obviously our future goal will be to shorten this up, because right now we need about like a 1.5 inch moment arm to get that necessary 100 pounds of force. So that's something we could definitely work on, getting that down, maybe modifying the housing structure to where you get that clearance of the clamp arm on the top, because that's going to be the main thing that drives how long that moment arm is. So just being able to make modifications to get that goal is going to be big.
Then we also did some stretch calculations just to make sure our gear set would be able to handle the load. And also we thought the idea of using plastic gears, but that should prove to be not able to take these stresses. Right now the safety factor is 1.4 with the aluminum bronze worm wheel, so it won't break on the first one, but the effects of wear and fatigue are still unknown. We'll figure that out in testing.
Alright, I'm getting into the electrical block diagram here. So all the red lines you see is going to be the power going into all our devices. We're going to start with the DC power supply. Then we're going to convert that down to 5 volts for the Arduino to run. That's also going to be connected to the driver, because that's going to have to run at 24 volts, which is industry standards. Which is going to be outputted to that stepper motor. This is more of a complex one here. So we have the 4 inputs going into our driver. Then we have our 24 volts voltage source, which is going to be converted, like I said in the last slide, down to 5 volts. Then we have the sensor A and B, which are going to be grounded because they are commonly, is there the reference point of the circuit? So that voltage change is that could affect our sensor reading, so we're going to put that to ground to make sure there's no sensor reading errors. And then we're going to have the 4 outputs going into the stepping motor for the clamping arm that actually work for us.
And then here's the outline of our controller design. the Excel step of the library is an Arduino library that gives us the abstraction to simplify our control. It allows us to track the motor position in terms of steps, and then it also allows us to run to a specified position just with a single command. And also, it changes the motor speed and acceleration, which is crucial to minimizing our cycle time and also outputting the maximum force. On the right there, you see a force, speed, torque diagram of our motor. For the majority of the cycle, when it's not contacting the workpiece, we're going to be running it at where the blue star is, so as fast as possible getting to that workpiece. But then once its contact is made, we want to slow down our speed and run it at the red star and output maximum torque, maximum force.
All right, so testing plan for the upcoming semester. Once we get all our components and build it, we're going to start by tuning the controller. Like Joe was saying, we're going to need to be able to adjust that arm speed and force, so that's something we're going to have to play around with and do trial and error to figure out what works for us. The effective gear backlash, we need that clamp arm to be in the top spot, the exact same position, and the bottom spot, the exact same position over cycles. So the effect of this could cause variance on that angle, so that's something we'll see through testing and see how we can make mechanical and coding adjustments as well. For the force test, to see if we're hitting that 100 pounds that we said we needed, we're using a force transducer and test that. And if we don't get that, like we said, we can make changes to that movement arm and make changes otherwise to see if we can reach that goal. And lastly, the cyclic testing for repeatability, not just fatigue strength and the wear of the gears that we were mentioning, but like we said, we need that position to be the same every time in the clamp arm. Otherwise, it's not going to perform its task as designed.
So getting into ethics and safety is the same one we always have to stand by. Our main safety reason is going to be if the user putting their hand near the clamp arm while it's closing. We're going to implement a sensor alarm to alert them that there is something there's something in the way, so don't go all the way down. And if that doesn't work, we're also going to have an on and off kill switch to make sure that turns off and no one gets hurt. Our future plans, we're going to modify the enclosure and clamping arms to reduce our moment arm, integrate limit switches. Of course, we're going to try to reduce our cost out of that 500 budget that we have. Order our parts by within a week or two. Write the controller embedded code for the circuit. Assemble the components by next semester and test functionality.
We'd like to thank Dr. Azabi, our advisor, and of course Dr. Bednarz for senior project class.
There's a couple of references.
Yes, I'm John Gilmer, retired. I have a question, and that is, you mentioned force transducer, but I didn't see it anywhere in the design work. I didn't see it in the Arduino circuit that showed the wiring. What is your force transducer, and how does it work?
So that would just be an external force transducer that reads like we would read it on there, and then based on, it wouldn't be integrated in the clamp at all.
It's not, so the clamp cannot tell what force it's exerting, is that right?
No.
Okay, thanks. It's open loop.
Yes. Dr. Jensen.
That's really fun. I mentioned many times in class that the motor is kind of needs moving. And you guys are dealing with a very tricky problem here because the motor is not heavy, the overheat when it's not moving. So that's something. But I'm glad you guys are using stepper. It's possible using stepper, but stepper, the holding torque is quite limited. You can use a bigger stepper to do this. It's possible. And stepper generally don't overheat that much. So the approach is very thorough. You guys did very thorough. So the approach is generally sound. But just like Dr. Gilmer was talking about, I strongly encourage you to put that little cell in the control loop. Use that for your control because that provides some very important information to make your control more flexible. Safety and many other things. It's not big investment. I think you're investing that for testing anyway. I strongly recommend you to put that in the control because you can do a lot with that signal. Because otherwise you're not open loop many unknown things. You can get things really out of control because you don't know what's going on in your system. So put that signal in your control is very essential.
We had talked about that, but it comes down to time constraints as well as budget also. So that's something we will experience.
You're already investing in a load cell here, transducer. You guys mentioned that. just that signal, just put that in PLC and do the control. It's not, there's no investment whatsoever.
Also, it would be integrated in the
Yes,
PLC.
yeah,
Okay.
you need that as a safety measure. For example, what if your force becomes too large? As a protection to your electrical system, that's essential.
Okay.
Thank you.
Following up on so the 1.4 safety factor is based on tensile stress of the platform.
So that would be the gear, the worm gear, so the bending stress on the teeth.
On the T.
Yes, sir.
Is it possible that before that point you will motor loop bridge? Do you have a locking mechanism for the car, you know?
So if the lead on that worm is shallow enough, which is ours is like 3.5 degrees, the documents that the gear companies they provide say that if it's under 4.5, it should be like you can't back drive the gear. So we're hoping it would be self-locking, so we could actually cut the power entirely.